Let's talk about the work-energy relationships. Now in class, I believe we've already derived the work-energy theorem. I think we've gone over all three relationships, but the work-energy theorem, the fact that the total work, or net work, acting on an object is equal to the change in kinetic energy of that object. And again, I don't know why they call it a theorem, because this is true because of the way work is defined and the way kinetic energy is defined. So work, if you recall, is force times displacement. If you're looking at the calculus version of it, that's equal to the integral of f dot dx. That is beyond the scope of 151, and so we don't really need to worry about that a whole lot. So we have work is equal to force times displacement. If the force is constant, you basically derive that. We have different types of work, though, because we have different types of forces. We have conservative forces and non-conservative forces. So conservative forces, we've only dealt with one so far, conservative force. It is the force due to gravity, or gravitational force. So gravitational force. And then non-conservative force is everything else that we've done so far. There is another conservative force that we will get to very quickly as we start talking about this, the ideal elastic force. Sometimes called spring force, but it's still an ideal spring, but ideal elastic force. So I generally use a subscript S for that because E we reserve for electricity, or electric. Electric force, and then in 152, so this is 151, in 152 we have electric force is conservative, magnetic force is conservative. Strong and weak probably are conservative, but that's well beyond the scope of anything taught here. So we have, so far gravitational force. And remember that we have two different types of gravitational force. Well, we have one type of gravitational force. We have two different formulas depending on the situation. If the acceleration due to gravity is relatively constant, in other words, if little g is relatively constant, then we generally call that, then we can use mg, so we know the value of g. If you're near the surface of the Earth, it's also known as weight. And then we have the generalized formula, the big G, mass 1, mass 2 over r squared. And so we have the two formulas. Now, it's called conservative and non-conservative because of how it treats energy. A non-conservative force will not conserve energy. A conservative force will conserve energy. And so we have the second relationship, which sort of hand wave through the fact that if I have non-conservative work, that's going to cause a change in energy. Now this energy right here is total energy. We have, so this E right here refers to kinetic, which we've defined already. It's capital K, the 1/2 mv squared. Now I didn't have to write 1/2 mv squared because you know it already. That is the one formula I do expect you to have memorized. And then there's potential energy, and the symbol for that is a capital U. Now, every conservative force has a potential energy formula. So if I ever ask, what's the formula for potential energy? The proper response is, which one? Now, which one depends upon which forces, conservative forces involved in the problem. If I have more than one conservative force, I'm going to have more than one potential energy formula. Unlike kinetic energy, if I ask what's the formula for kinetic energy, 1/2 mv squared. So if we have the net work is equal to the change in kinetic, and the non-conservative work is equal to change in energy. One thing before I jump into that next bit, so this is, if this is the total work, this is the total force. If this is non-conservative work, this is equal to the non-conservative force times displacement. If this is the conservative work, that's equal to the conservative force times displacement. So as we look at these relationships here, the rest of them, this energy right here, and I need to erase some stuff, so hopefully you have that down. The total work is equal to the change in kinetic energy. Well, the total work, so we'll just start with the net work, is equal to change in kinetic. This is equal to the conservative work plus the non-conservative work is equal to the change in kinetic, because those are the only choices. The total work has got to be the total conservative plus total non-conservative, because there's no third option. The non-conservative work is equal to the change in total energy, so this becomes work conservative is equal plus the change in energy is equal to the change in kinetic. Energy is just potential plus kinetic, so this is the conservative work plus the change in kinetic plus potential is equal to the change in kinetic. The change in this is just equal to the change of each. In other words, work conservative is equal to, plus the change in kinetic plus the change in potential equals change in K. And so now kinetics cancel out, and what I'm left with is the conservative work plus the change in potential energy is equal to 0, and the conservative work is equal to the negative change in potential energy. So we have the three equations right now. When I talk about in class the work-energy relationship, we have this one right here, we have this one right here, and we have this one right here. Those are the three work-energy relationships, and we will exploit these definitions and these equations coming up. So that's what we have right there, and so we will now jump into a problem. We'll actually derive a potential energy formula. We'll derive one of them, and that will be the next video.